Anthropic, the company that just declared that coding is solved, is actually still hiring software engineers, and their interview process is quite brutal. For a long while, FAANG companies were famous for their rigorous interviews and hiring pipelines.
Sit.
If you wanted to work at any of the giants, you had to survive algorithmic whiteboard sessions, system design interrogations, and behavioral rounds engineered to test both competence and composure under pressure. It was so famously difficult that services were created just to guide you through that process. And, based on the recent experience someone shared on Reddit, it looks like Anthropic decided to import the entire FAANG playbook and then add a few extra levels of difficulty just for the fun of it. So in this Monday morning review, we'll stop discussing the future of AI in software and we'll review the technical expectations of the hottest company in the tech industry. The interview process, while fascinating, has a high degree of complexity because Anthropic has the luxury of targeting the top fraction of the talent pool. And, while there is almost no chance for you or I to actually end up working there, the technical aspects are still useful for anyone involved in software development. The interview was for an infrastructure software engineering role, and it had 5 rounds over the course of 3 weeks. The first round was a classic online assessment with 2 problems in 90 minutes. The aim with this initial assessment is to eliminate everyone who can talk about software topics on their YouTube channel, but can't implement a hash map without googling a bunch of details first. So this is where I'm usually failing my interviews. The first task was to implement a least recently used cache, which is a pretty standard cache eviction policy. A cache has limited capacity, so when it becomes full and a new item must be added, one existing item must be removed. LRU removes the item that has not been accessed for the longest time. So the core idea is simple. Every time an item is accessed, it becomes most recently used, and the item that goes the longest without being accessed is evicted first. A naive implementation would store the elements in a regular map and, on every access, iterate through the entries to figure out which one was touched least recently. This works functionally, but it destroys the whole point of a cache because the time complexity becomes linear and your optimization becomes the bottleneck. The expected solution is the canonical one using a hash map combined with a doubly linked list. The hash map gives you big O1 access to elements by key, and the doubly linked list maintains the usage order. If you are not familiar with them, doubly linked lists are linear data structures where each node contains 3 fields: the stored value, a reference to the next node, and a reference to the previous node. Because every node knows both its neighbors, you can remove a node from the middle in constant time. So when a key is accessed, you move its corresponding node to the head of the list. When inserting and the cache is full, you remove the tail node and delete its entry from the map. The second problem of the online assessment was a task management system with priorities, worker assignment, dependencies between tasks, and cascading cancellation. A key detail here is that each task could depend on other tasks. That immediately implies a directed relationship. If task B depends on task A, then A must complete before B can run. The correct abstraction here is a directed acyclic graph where nodes represent tasks and edges represent dependencies. Once modeled as a DAG, the execution order becomes a classic topological sort problem. You compute an ordering of tasks such that every task appears after all of its dependencies, and with a depth-first search approach, you can get it solved in linear time. Priorities complicate things because among the tasks that are currently eligible to run, you need to pick the highest priority one. That effectively means combining topological sorting with a priority queue. For cancellations, if task A is cancelled, then every task that depends on A directly or indirectly must also be cancelled. In graph terms, that means traversing all reachable nodes downstream from A and marking them as invalid. This concludes the first of the 5 interview rounds. If you are already feeling lost, don't worry, this is completely natural. People spend years deliberately training for this style of interview. The second round is where things get a bit more interesting, because now you have to prove that you can build something that behaves like real software in the wild. The task was to create a crawler, probably to steal training data for the next cloud version. You had to start from a given URL, perform a breadth-first search, crawl up to a certain depth, extract the links, deduplicate the URLs, and build up a site map, all while rate limiting yourself to avoid accidentally DDoS someone's blog. When implementing the solution, you'll need a queue initialized with the start URL. Then, for each URL you remove from the queue, you fetch the page, extract all outgoing links, normalize them, and enqueue the ones you haven't seen yet. Of course, you need a visited set, because without it, you loop forever. The web is a graph with cycles everywhere, and even small sites contain self-references, circular category links, or pagination loops. Rate limiting forces you to think about throughput control, because you can't just fire off unlimited requests. So you can use a semaphore to control current fetches. A semaphore is a simple way to limit how many things can run at the same time. Think of it as a counter. You start it with a number like 5, which means only 5 operations are allowed to run concurrently. When a task wants to do something controlled, it first tries to acquire the semaphore. If the counter is above 0, it decreases the counter and continues. If the counter is already 0, it has to wait. We are getting now into the concurrency territory, which is a beast of its own and was one of the main focuses in the interview process. However, things are already difficult enough, so we'll just pretend concurrency is a solved problem. The next part of the interview is the most important one, but before discussing the system design topics, please let me tell you a few words about today's sponsor, JetBrains. I've been a long-time user of their products, and today I want to talk to you about Juni. Juni is a coding agent designed to help developers automate parts of their workflow. You can delegate tasks to it, ranging from small things like generating tests or boilerplate, to larger tasks like refactoring parts of a codebase or scaffolding a backend service. And now JetBrains has released Juni CLI, which brings that same agent directly into the command line. So instead of being locked into a specific interface, you can run Juni directly from your terminal, integrate it with your existing tooling, or connect it to your development workflow. Juni CLI uses the same brains that power IntelliJ IDEA, so it inherits the same understanding of codebases, project structures, and development workflows that JetBrains has been refining for years. It also supports multiple large language models, and you can either choose the model yourself or let Juni automatically pick the most appropriate one for the task you're trying to complete. Please check out the link in the description to find out more about Juni. The next round was system design, and this is where things got really interesting. The task was to design an inference API for serving large language models, which is literally the kind of infrastructure Anthropic builds every day, so the discussion went deep very quickly. The first challenge is that requests are not uniform. One user might generate 10 tokens, another might generate 10,000. That means requests have completely different runtimes and resource requirements, so the system needs a request queue that can handle variable length workloads and also supports priorities. But the real constraint is the GPU. Running one request at a time would waste most of the GPU's capacity, so inference servers rely heavily on batching. In other words, multiple requests are grouped together so the GPU processes them in parallel. The tricky part is how you form those batches, because if you mix very short and very long requests, the shorter ones get stuck waiting for the longest request to finish. So, a good batching strategy groups requests with similar expected lengths. That usually means estimating the workload based on prompt size and maximum token generation. Key-value cache management also came up. During generation, language models store intermediate attention states in a key-value cache so they don't have to recompute previous tokens. This speeds things up dramatically, but the cache consumes GPU memory. With many concurrent requests, managing that memory becomes critical. And, of course, streaming responses add another complication. Instead of returning a result at the end, the system streams tokens back to the client as they are generated. That means each request becomes a long-lived connection that continuously produces output. The second coding round was again focused on systems territory. The task was to take the output of a stack sampling profiler and convert it into a trace format that could be visualized as a timeline of function executions. To understand the problem, we need to briefly talk about how sampling profilers actually work. Unlike instrumentation profilers, which modify the program to record every function entry and exit, sampling profilers work by periodically interrupting the program and capturing the current call stack. Each of these samples tells you what the stack looked like at that exact moment, but it does not explicitly tell you when functions started or finished. The challenge is to reconstruct those events. The typical solution is to diff consecutive stack samples. You compare the two stacks from the root until they diverge. Everything deeper than the divergence point in the previous stack must have exited. Everything deeper in the new stack must have started. The final round is not that interesting from a technical standpoint, so here we are. Let me know your thoughts about these problems in the comments, and until next time, thank you for watching.